Hello, I'm Bongani Shongwe, and I'm here to present to you about running an open source large language model on your own infrastructure. I first want to kick off with a short introduction about the company I work for at Aventa and what is it we do. Because a lot of people might know about our secondhand on-site marketplaces, but they do not know much about the brand Adavanta behind them. Adavanta is one of the world's leading online classified specialists with market across three continents, containing over 25 marketplace brands. Our marketplaces range from consumer goods, vehicles, real estate, and jobs. Adavanta consists of several marketplace brands like Kleinzeigen in Germany, Marktplaats in the Netherlands, Leboncoin in France, Kijiji in Canada. Adavanta is a champion for sustainable commerce, making a positive impact on the environment, the economy, and society. By the numbers, we get about 2.5 billion monthly visits across our website. We have 25 plus marketplaces in our digital portfolio and over 5,700 employees across 10 continents. Now, at Elementor, we've been working on Conversational Search Assistant, which is geared to launch on Leboncoin France for A/B testing during the second quarter of this year. Conversational search is about building a smarter shopping experience by allowing users to ask arbitrary questions and being guided to relevant recommendations and search results by an assistant. In order to serve a greater user experience outside of the normal chatbots, which are in use by most websites, the conversational search assistant will be backed by a large learning model service. Conversational search can be defined as a chat interface to enhance the user experience by allowing natural language interactions with software agents or virtual assistants to retrieve information. The product we envisioned is kind of like this. This is an example I drew up. Um, and with the conversational assistant, when it pops up or when you interact with it, you'll ask it a general question. In this case, this user is looking for a Ford Focus or a Fiesta. And it's for the conversational search assistant to assist the user in narrowing down the search products and also asking for more preferences in what the user would like is specific in this vehicles he's looking for. Basic infrastructure overview of how it would work. The user would get would of course interact with the conversational search assistant, and which would in the background generate a query to call a conversational large learning model. The large language model also gathers the history of the conversation which has been happening, and it extracts that information in order to consolidate it and push the information to a search API to get relevant search results. This this everything here, the conversation large language model and the extraction large language model is backed by ChatGPT 3.5. Outside from OpenAI, the team has also been looking at other providers for large learning model APIs. However, we found that there are some downsides in having to use a service provided large learning model. Some points are the readiness of the service, as this is still a new field, and some providers are slow to open up to more customers to a larger scale. Thus, it takes quite a while to get onboarded onto these services. There's the cost factor. Of course, this is a new additional cost for the team and the company. And we also had to think about latency. Given that the service is outside of Adavanta infrastructure, there's an additional latency we have to account for. Given some of these factors, we decided to investigate the use of open large language models, which we could possibly deploy into our own infrastructure. So during the proof of concept phase, where we're using paid go-to services, we also started exploring looking at hosting a large language model. With an enterprise service, you get the top your best quality and the latest large learning models which are being produced. And yeah, versus for us, when you do a self-hosted solution, you have the benefit is that you're in complete control of your application, and on your team is responsible for the system. By versus using an external API, you're dependent on that other system being up all the time for your service to run. Some benefits in using um, another your own hosted large language model is that you have greater privacy and compliance, and you also avoid vendor lock-in. We started exploring models to use by going to Hugging Face. Hugging Face is currently the main platform or a website for building and using machine learning based models such as large language models. It also provides a platform to run these models on a smaller scale. In our case, we considered text generation based models. We first started off with the Falcon 7 billion meter parameter tuned model to get familiar with deploying a large language model. It's a lightweight model, and it's quite easy to get started and set up. Though it is lightweight, we did find it lacked depth when answering specific questions, specifically when we're looking at to use it for as a conversational search assistant. So then we started looking at other models which were out there, which we could use. We looked at the Falcon 40 billion chat tuned model and the Llama 2 70 billion chat tuned model. This, aside from being chat tuned, these models also provide multi-language support, which was a requirement for us as our marketplaces are across different countries with different language customers who speak different languages. So uh, on deploying the model or hosting the large language model in this case, we found text generation interface or TGI. For short, TGI is a fast optimized interface solution built for deploying and serving large language models. TGI enables high performance text generation using tensor parallelism, dynamic batching for most popular, and dynamic batch for most popular open source large language models. TGI also has a Docker image which can be used to launch the text generation service. Some of the benefits we found using TGI is that it's a simple launcher service to host your model. It's production ready as it provides tracing with open telemetry and Prometheus. There's token streaming. You can have continuous batching of incoming requests for increased total throughput. There's quantization with bits and bytes, stop sequences, and yeah, you can have custom prompt generation, and you can also it also provides fine tuning support to fine tune your models. The easiest way to get started with the text generation interface, for text generation inference, is to run the simple command line, which is you just point to the model which you'd like to use. You set up which where to store the model and all the data such as the model weights. And when you run this, it's a Docker command. It'll launch the TGI Docker, and if your model is not present on your machine, it'll download it. If it is present, it'll just it'll start running. And to get going, you can just to test it out, you can use a simple curl command, and as you can see, uh, you submit the JSON and you'll get a response from the model. Now, our team based our experimentations on GCP. Initially, we tried to run the deployment on our European region of GCP. However, it appears that with the rise of GPU use applications such as large language models, there's a scarcity of GPU availability in Europe and North American regions. Actually, if you research this more, it seems to be occurring across all the cloud providers because of the current popularity of just GPU based applications. So we scanned outside of Europe and North America, and we found that there were two zones that could provide GPUs which we could get for spot instances, and those were in the East Asia, and also in the Middle East one, to be specific. Large language models require high GPU to train. For inference, it can be less, but it's still generally a large amount of GPU memory required. The higher parameters the model contains, the more GPU memory required to run the inference of the model. There's also the possibility to run the model inference in 8 bits and 4 bits mode, which decreases the amount of GPU memory required. Based on current GPU availability in cloud environments, the best options are machines that contain NVIDIA A180 gigabytes. However, these GPUs are extremely scarce even in the cloud environment. We had then settled for using machines that contain a NVIDIA A140 gigabytes. It is also possible to run a model on multiple GPUs in order to meet the memory requirements of the model inference. So there's two ways we could have deployed these models and the TGI inference. The first one was using Kubernetes or running it on a virtual machine. For doing it on Kubernetes, we just created a simple a deployment YAML, and we allowed for auto scaling because we didn't want to keep track of all the machines. So this seemed a bit better because when the models are not in use, it's easy to downscale. As versus for if we're going to do it with using a virtual machine, these were self-managed machines, and we'd have to keep track if on the capacity. Basically, if machines were not being used, then we'd have to shut them off ourselves. So we went into because of this, we specifically started looking with doing it on Kubernetes on GKE. This is kind of a high level overview of a GKE setup. You'd have the text generation inference deployment running in a Docker image, pointing to a volume where all the weights were fetched from GCS. But we actually came into an issue when we started using GKE. As we started, of course, we started with the Falcon 7 with the lightest Falcon model. Even with that, we found that the deployment time took longer than expected. GPU machines were also not ready available for use, even with Kubernetes. And the highest the highest GPU machine, or in this case, node, a GPU node, which could be hosted with, we were able to get with GKE was a 12 gigabyte GPU, which was not enough to push on with the other large learning models. So given that, we went back and said, well, we're going to do the virtual machine deployment strategy. Yeah, and with the texture inference, it allows you to host the model on a VM with a single GPU or parallelized inference across multiple GPUs. One of the benefits of parallelizing it across multiple GPUs is that you can meet using multiple GPUs. You can actually have more higher memory across all the GPUs for inference. We started looking at running our experiments, and we set up our experiments when we deployed the models in a virtual machine. We set up notebooks to run different experiments so we can be able to track the data and compare the results later on. Yeah, so we looked at, so we had different cases where we deployed the models on a single a VM with a single GPU and a VM with multiple GPUs. Yeah, we had for the single VM, we had a short response latency, which was really perfect for us. The deployment was quite quick, and but the number of max tokens which could be processed was limited to the GPU memory. With a VM with multiple GPUs, we increased the GPU memory footprint, so we had more GPU memory, uh, and this in turn increased the max token processing. The time it took for the model to be ready increased, so the deployment time also increased, and the response latency also increased. There were several factors which we looked into why latency, the factors which came into latency with this. And some of the during our experience, we found out that it was due to prompt size and complexity. So similar to if the prompt was long and quite complex, it will take longer for any of the models to process. However, the less indirect and short prompts it is, it opens up the ability for side effects such as hallucinations. For specifically with latency, for with GPU setup, we track this down that using more GPUs across VM with more GPUs increase the latency. We figured out that this could be between that there's a lot of I/O happening between the GPUs, so there's a lot of data exchange happening versus when you do an inference on a single GPU machine. And another thing which we tracked with regards to latency is the max token output. So we were able to set the max token output of the deployment. And the higher the token output length, the response from the model becomes more detailed and longer, which requires more processing time. But if the token length is extremely short, the response time might not be complete or make sense to a human. Thus, there has to be a balance between how detailed the model response is and the quickness of the response. And more detailed analysis on this. Yeah, as I mentioned, it is possible to set the number of tokens used for the output. All the previous tests we've done, we set the token outputs to 256. And by once we doubled it, we were able to observe different effects from the models tested. So for the Falcon model, with 256 tokens, maximum tokens, the model seemed to perform adequately. Once we increased the number of tokens, the response time initially seemed to be the same as before, but as the conversation continued with the user, the response time began to increase. Another effect was that the response became longer and the model had started to hallucinate, appearing to have a conversation with itself. Llama 2, we also again started with 256 maximum tokens, and the models performed adequately, but we'd note at some instances that the text response would appear to cut off. And with an increase in the token size, the latency also increased quite extremely. And the response was more complete, but as the conversation would continue, we'd get some instances where the response would get cut off again. And as I mentioned again, we have marketplaces across different countries or different languages. So it is important for us to test how this performs. And since we're launching first in Devon, we looked at using French. So we tested the Falcon and Llama 2 on its ability to do inference with French users. The main adjustment was with the system prompt, directing the model to respond only in French. For Falcon, if the user's question was in English and the model proceeded to respond in English. But if the user asked questions in French, the model responded in French. And if the preceding user questions was in English, the model remained only speaking in French. And if all the user questions were in French, the model stuck to respond to French. However, there were some side effects we observed and some hallucinations of within the model when using the French language. In the case of Llama 2, if the user's first question was in English, the model proceeded to respond in English. If the user's first question was in French, the model responded in French. However, if the preceding questions were switched to English, the model reverted to responding in English. And if all the user's questions were in French, the model stopped responding in French. And what we can conclude from this is that both models are quite adequate in responding to users in French. One thing to note here is that within our discovery, we found out there's no one-to-one switch between using different models. It is not easy to switch using the same prompts or techniques in one conversational search large language model and use it with another without experiencing any type of side effects. For example, the prompts we used for these experiments had to be adjusted to what we're using with OpenAPI conversational search large language model. And though these experiments showed points of success, for more adjustments we needed to get responses to the quality. We need to do more adjustments to get responses to the quality which we're using with OpenAI. We also adjusted properties to launching the model service and the properties of the API calls, but we did not do an in-depth evaluation with these properties. It is evident that with some slight adjustments, the latency and quality of the large language model changes, but further investigation would have needed to be done by a team to find the best properties for our required results. So you might be the big question is how much is this all going to cost you? In our experiments, we're able to run the models on a single A140 40 gigabyte GPU, and the cost calculations for that model for using a model would come around to around just under 3,000 US dollars a month. But since we have discovered that having more GPU is an advantage, we would need to select the highest GPU available, with being the NVIDIA A100 80 gigabytes. And that would come down to around of a cost of 4,200. This estimation is for a single instance. If we were to scale out using Kubernetes autopilot or manually adding more VMs, the cost of running the open large model would grow significantly. It's also good to note that these costs do not include human costs or networking costs and maintenance costs. So in our exploration phase, we looked at hosting a large learning model and comparing it to an enterprise large learning model. The downsides we actually ended up coming out of is that it's difficult to get adequate GPU, and that there's a lot of high cost associated with running this model. It also would require internal support or expertise, and also security maintenance. On the other side, while we were running this proof of concept, we had come to the discovery that, OpenAI actually announced that they were decreasing the cost of ChatGPT 3.5 Turbo, and this made it more promising to use. And as for the slow AI API response time, we are also doing some fine tuning on the model, and by doing some fine tuning, it actually sped up the response time. So my learnings and outcome from this from deploying a large language model. Yeah, it's definitely possible. Uh, Based on a use case and based on our use case, it's best to start off with a lightweight model like the Falcon 7 billion meter parameter tuned one, and start using that internally. Just discover, play with it, and figure out uh, what properties you can use to offload or what functionality you can use to offload to your internal model, and use that and slowly start offloading to it until you get to a stage where you can either have a balance of a pay to go service or have or having fully running it on your own infrastructure. Thank you, and I hope you enjoyed the talk. If you have any questions, please feel free to get in touch with me.